So, hello everyone. I'm Liesa Berisha, and I'm an independent researcher from Kosovo with a deep focus on theoretical physics, specifically the structure and symmetries of spacetimes in higher dimensions. So, today's topic is Bondi-Meissner-Sachs symmetries in dimensions greater than 4, central extensions, algebraic obstructions, and the BMS-GCA correspondence within asymptotically flat holography. Okay, so in Einstein's theory of general relativity, spacetime isn't just a passive stage, it's dynamic, flexible, and filled with deep symmetries. One remarkable example of this is the Bondi-Meissner-Sachs group, which describes the symmetries of spacetime at null infinity, which is known as the boundary where outgoing light rays escape in asymptotically flat universe. So the BMS group is originally formulated in four-dimensional spacetime, so these symmetries have become a central part in our understanding of gravitational radiation, memory effects, and even proposals in quantum gravity and holography. To better understand this BMS symmetry, I will use a simple analogy. So, imagine you're watching waves ripple out from a pebble dropped into a calm lake. So, just like those waves spread outward, gravitational waves ripple through space when massive objects like black holes collide. So, now picture the very edge of the lake, the place where waves disappear into the distance. In physics, that edge of spacetime is called null infinity, and the BMS symmetries describe the special rules that apply out there, far away from everything. So the original BMS group arises as the asymptotic symmetry group of four-dimensional asymptotically flat spacetimes. So that is spacetimes that are very far away from any sources, being to resemble flat Minkowski space. So now to understand how BMS fits into the bigger picture, let's recall the Poincare group. So this group is the backbone of special relativity. So it combines translations in time and space with rotations and Lorentz boosts. So the Poincare group includes all of these transformations plus an infinite number of new ones called supertranslations. So these are angle-dependent translations at null infinity that reflect the presence of gravitational radiation. So this group has two main components, as we have assessed before, supertranslations that are like regular shifts in space and time, but instead of being the same in all directions, they vary depending on the angle. So you can imagine this as shifting points outward along rays of light, but by different amounts in different directions. And then we have superrotations, which go beyond the usual idea of rotating or boosting a system. So in four dimensions, spacetime symmetries are described by a Lorentz group, the group that includes all standard rotations and motion at constant speeds. So superrotations extend these by allowing any smooth, flexible transformation of the celestial sphere, which is the imaginary sphere at infinity where all light rays arrive. So another key element in understanding BMS symmetries in higher dimensions is the role of boundary conditions. So if we loosen up or relax these boundary rules, something more interesting happens. So a richer set of symmetries emerges called the generalized BMS algebra. So this extended structure includes what's known as ultra-hyperbolic BMS groups, which explore symmetry in spacetimes with unusual or mixed signatures. So now let's connect this idea with black holes. In higher dimensional physics, we also have solutions that describe rotating or static black holes, generalizations of the familiar Schwarzschild metric, which also describes a simple, non-rotating black hole in four dimensions. So by rewriting these higher dimensional black hole solutions in a special form known as Bondi coordinates, we can better analyze their symmetries at infinity and define new kinds of conserved quantities, or also known as charges associated with the BMS groups. Okay, now we will talk about the evolution of BMS group and its symmetry, which can be assessed through various major chronological stages. So the first one is the early discovery and definition, which happened in the late 1950s and 1960s. So the BMS group was discovered through the work of Hermann Bondi, Miji C. van der Burg, Metzner, and the famous physicist Sachs. So the BMS group was identified as a group of asymptotic symmetries of asymptotically flat four-dimensional spacetimes at null infinity. So Bondi mass was defined as a conserved quantity in the absence of gravitational radiation and was later extended to four momentum. Bondi mass loss formula is linked to also the charge with respect to time translations, which represent the energy of the system. Later, the famous physicist Roger Penrose contributed to an important geometric interpretation of the BMS group. So he showed that the BMS group was an exact global transformation group acting on future null infinity and introduced by conformal compactification. Later, we have the representation theory and its physical meaning, which happened in the 1970s. So, on Wigner's program from the Fourier group, P.J. McCarthy systematically classified the strongly continuous unitary IRS, which is known as irreducible representations, of the BMS group in the early 1970s. So McCarthy later his classification of the IRS depended on determining the little groups. So crucially, the choice of topology on supertranslation space, whether to choose the Hilbert or the nuclear topology, is really important in ordering the classification of BMS representations. Then we have the extension to higher dimensions, which happened in 2000s and 2010s. So it initially focused on four dimensions. The concept of BMS symmetry has also been extended to higher spacetime dimensions, but there are significantly different differences between dimensions in greater than four and dimensions equal to four. So the number of supertranslations has also been demonstrated to expand to dimensions equal to four and dimensions equal to five. So the number of supertranslations is 4 at dimensions equal to 6 because possibly new supertranslations define proper gauge transformations. So this trend is anticipated to hold for dimensions greater than 5. And then we have the modern renaissance, which happened to 2010s and still is continuing till today. So the gravitational memory effect is the permanent shift of test particles due to a burst of radiation, and dimensions equal to 4. This is a direct result of BMS supertranslations. However, this is a feature of general relativity and is specifically in 4 dimensions of spacetime. So our methodology it also leverages explicit examples of higher dimensional black hole solutions, such as Kerr and Schwarzschild metrics, which we later discussed. So furthermore, a critical aspect of our approach involves exploring the correlation of these symmetries with the context and thermodynamic properties. So also this exploration aims to contribute to a coherent quantum gravity paradigm in asymptotically flat spacetimes. So it proposes connections between volumetric attributes and surface symmetries rooted in holographic principle. So the Bondi-Meissner-Sachs symmetry was first discovered as a group of asymptotic symmetries, describing how spacetime behaves very far away from any matter of energy. So mathematically, the generalized BMS algebra is much more intricate or complex than the original four-dimensional case. So understanding the generalized BMS symmetries in higher dimensions is key for progress in advanced symmetry theories of gravity, including higher spin gravity and holography in flat spacetime, which is an area of research that aims to relate gravitational physics to quantum field theories in a new way. So the analysis notably reveals a linear deformation of the semi-direct product of the Lorentz algebra with an abelian group. So the nonlinear deformation mentioned stems from the intricate interplay between these supertranslations and the Lorentz generator. So in 5 dimensions, leading and subleading supertranslations form canonically conjugate pairs. So this unique characteristics enables a supertranslation and varied redefinition of the Lorentz generators. So this redefinition effectively decouples the supertranslation form of the Poincare algebra. So it implies a more complex nonlinear modification of the Lie algebra structure beyond just a simple semi-direct product. So the BMS GCA correspondence highlights a significant connection between the asymptotic symmetries of flat spacetimes and non-relativistic conformal symmetries. So the connection between BMS and Gillian conformal algebra, also known as GCA, can be understood through specific limits. So this is analogous to how the Poincare symmetry follows the anti-de Sitter spacetime in 3 dimensions. So in fact, Poincare modules can be seen as frenantines of the SO2 to 2 representations, those and whose energy becomes large in ultra-relativistic limit, where the speed of light tends to go to infinity, or equivalently, so the anti-de Sitter spacetime radius tends to go to infinity. So this contrasts with non-relativistic limits, which typically yield non-unitary representations. So the connection between BMS symmetries and Gillian conformal field theories comes from trying to apply holography, like the famous ADS-CFD idea, to flat spacetimes. So a key idea behind the link is Carolean geometry. So think of it as what happens if you take the speed of light and imagine it going to zero. So an ultra-relativistic limit of usual spacetime geometry. So because of this, the math describing BMS symmetries matches perfectly with that of the generalized CFFTs in certain dimensions, meaning their algebraic structures are basically the same, what we call in physics as isomorphic. So now the operator product expansions, or OPEs, are a fundamental tool to use in conformal field theories to analyze how operators behave when they come closer together. So these OPEs also turn out to be very useful when applying and studying BMS symmetries. So this research identifies several important gaps and challenges in understanding generalized BMS symmetries, especially in higher dimensions. So the first one is no geometric null infinity in odd spacetimes where dimensions are greater than 4. So through this research, we defined conserved charges for supertranslations in dimensions greater than 4. We've assessed soft superrotation charges, complete radiative phase space for nonlinear gravity. We've assessed representation theory of BMS algebra and also the superrotations in higher dimensions. So the Neat-Versaro-like structure seen in 4 dimensions, superrotations, is absent in higher dimensions, which very much complicates their understanding. Okay, so to further close this, I just want to briefly also reflect on the range of resources I use in this research. So the references span a wide spectrum from foundational papers on BMS symmetries and their original formulation. So altogether, these references help me understand not just the technical definition, but also the deeper physical motivations and the unresolved questions that keep this field very much alive. So the study of BMS symmetries and their generalizations opens exciting new windows into our understanding of gravity, spacetime, and the deep connections between geometry and quantum theory. So I hope this presentation has given you a clearer picture of why these infinite dimensional symmetries matter, not just as abstract mathematics, but also as fundamental aspects of shaping the nature of our universe. So thank you all for your attention, and I'm happy to answer any questions. Thank you.